Hello, hello. Welcome back. Another episode. I need to drink some water. Hang on. My voice is being destroyed by the video making process. Oh, joy. Yeah. So, electrochemistry and cell potentials on spontaneity is today's topic. Um, Voltaic cells generate an electromotive force that causes electrons to move from an anode to a cathode via an external circuit. Cell potential is the difference of electrical potential between two half cells of a electrochemical cell. So it measures the difference in potential energy of an electron at the anode and the cathode. Cell voltage is interchangeably used with potential. The unit is a volt, which is equal to joule per coulomb. So, or more for physicists that's probably more useful, but for chemists it would be more appropriate to say how much energy is transferred per electron, and it's related to delta H. It's not delta H, but it's related. It would probably be related. Um, there's probably some relation there. Um, Cell potentials, you generally determine them experimentally using a voltmeter. Um, for half cells, that's what you have to do. Uh, and then you determine them using a voltmeter uh, under standard conditions, which are 25 degrees, 1 molar, and pressures of 100 kPa. Cell potentials are Cell potentials of working voltaic cells, i.e., based on spontaneous reactions, are always positive. The spontaneous redox reaction is the source of electrical energy generated by the voltaic cell. A cell can theoretically have a negative value if it was based on a non-spontaneous reaction, such as a electrolytic cell. However, generally you don't tend to. That's the only way you can get a negative cell potential if it was a electrolytic cell. Um, the half cell potentials, it's not convenient to basically measure every single thing, so we tabulate it on half cell potentials. So cell potentials that are measured by adding the half cell potentials together. So the electromotive force of the cell is equal to the electromotive force of the oxidation plus the reduction. Um, uh, note that in the table that you're given, they are all reduction potentials, not oxidation potentials. And in order to get oxidation, you have to flip it. You have to flip the one for oxidation. You keep the reduction one the same, but for oxidation you flip it. Um, there's a whole set of it works similar to like Hess's law questions, except there's one key difference, which I'll go on later to talk about later. Anyways, I'm getting ahead of myself, but since you can only really measure the potential of a cell, you have to measure it relative to some sort of standard, and the way we do that is we measure it with respect to the standard hydrogen electrode, which is a platinum electrode in contact with 1 molar concentration of acid and 100 kPa H2. And this one has been arbitrarily assigned 0, so i.e. this half reaction here and this half reaction here are both assigned a cell potential of 0 volts. And as a result, when a standard cell potential is measured using the standard hydrogen electrode, and the reason platinum is used is because it's not reactive and it would have no effect on the redox reaction. So here's sort of what we described with the standard hydrogen electron. So here's your half cell, and then salt bridge, and then here is the standard hydrogen electron. This is the piece of platinum they use to connect to the wire. It's immersed in nitric acid, and then you bubble in H2 gas here to expose it to hydrogen. So um, that's sort of how you tabulate. That's sort of what we use in the real world. We tabulate all these half cell potentials, and then if we want to get the voltage of a specific reaction, okay, we just add the the oxidation half reactions cell potential and the reductions half cell potential. That's sort of how we go about it. Um, so to determine cell potentials, the appropriate redox reactions must be added together. Um, if you flip the reaction, you flip the sign. However, if you multiply it by a scalar, the potential does not change. What does change is the amount of energy released. However, remember, voltage is energy per electron, and you don't change the energy bit, you change how many electrons transfer overall. So, although more energy is transferred, the amount of energy per electron is the same. You just have more of them. Uh, Here's a table of half cell potentials. So here's a table of half cell potentials. The IB gives you one of these as well, but we can see here that fluorine has the strongest reduction potential since it is a strong oxidizing agent and likes to be reduced. And then similarly here with lithium, we have a very low reduction potential here because it is the lowest, it has one of the lowest ionization energies, and therefore we consider it to be a weak reducing agent. Weak reducing agent, and it is therefore, no, it is a strong reducing agent, it's a weak oxidizing agent. Oops. Yeah. So the next thing I want to mention is that relates cell potentials to the Gibbs free energy, or the spontaneity of a reaction. A positive cell potential indicates a spontaneous reaction. A negative cell potential indicates a non-spontaneous reaction. This intuitively makes sense. For a voltaic cell, the forward direction is very much favored, and the forward reaction is typically positive, so it makes sense that that's spontaneous and would happen without any outside intervention. However, to sort of now, although that's very good, positive cell potentials are spontaneous and therefore have a Gibbs free energy change that is less than 0, and the inverse is true. That's great. However, we need a mathematical formula to relate the two, which we get if we scroll here. We get this formula here, which is the Gibbs free energy is equal to negative n times F times E, where n is the number of moles of electrons that are transferred in the redox reaction. F is the Faraday constant, which is given in your data booklet, and delta G is the standard Gibbs free energy change. Here's a little table relating all the possible signs and stuff to electromotive force of a cell and the Gibbs free energy. Just remember this equation, but what you just need to remember, what I think is probably most important to remember, is that this and this are proportional, is negatively proportional. This is proportional to the minus of that, so that's what you should remember. And that is all there is for today. Thank you for watching, and we'll see you in the next video.